You have about 1 billion particles of dark matter flowing through your body every second.
How come we haven't figured it out yet?
The reason why we can't just say, oh, let's go and discover where dark matter should be, is that dark matter is a concept. It's a phenomenon that we observe, but we don't have any idea, number one, if it is a particle. But if it is a particle, we don't know what the mass of this thing should be. And the mass of this dark matter could be over an enormous range. It could be having a really, really tiny mass. It could have enormous masses that are like several times the mass of the Earth. The reason why dark matter has been so hard to discover is that we don't really have a good kind of theoretical hint. And that's super weird because we have kind of had these all the time in the past for physics. I'll give you an example of what I mean. So this particle we discovered back in 2012 here at the Large Hadron Collider is called the Higgs boson. Sometimes in the press, it's referred to as the God particle. The existence of this particle was predicted way back in the 60s. And in fact, it turned out that it was there waiting for us to discover all along, but we had never built a large enough experiment to discover it. There's a lot of these in the past where it's like, oh, the big open question is blah, blah, blah. Oh, and the theory says you should be able to find so-and-so to explain blah, blah, blah. And we did that experiment and there it was. This has happened like in the 80s, and honestly, in the 20th century, this is kind of like clockwork the way it happened. So that's why it's both scary and also kind of, wonderful to be a physicist at this moment, because we have huge open questions and we're really out of like the big theoretical hints, like the flashlights. It's like, chink, go over there. And that's where your discovery is. We don't have those anymore. And we have to, look in all possible places. We looked for dark matter everywhere. We look for it here at the Large Hadron Collider. You can also look for it, say, in direct detection experiments. And that means exactly what I said. So for example, I told you, probably you have about 1 billion particles of dark matter flowing through your body every second. This means that your body is just a bad dark matter detector, right? So what we're waiting by detector, what I mean is that eventually one of these dark matter particles has to bump into something, you or so, like a detector apparatus. And if it does actually bump into the particles that make up you and I, that would mean that it's bumping into us probably by a new force of nature. And that would be fantastic because it would give like a little signal. We're like, oh, okay, because what we're looking for is extremely rare.
So if we figure out this dark matter, right, that 95% of the universe, or the number that you said, if we figure that out, then what changes?
What would change is hopefully it would deepen our understanding of what the universe is made of, for obviously, right? So, I mean, that's at the end of the day, that's like a big open question for science that it seems obvious we'd have to solve, right? If I tell you, we are very good at, as physicists, as astronomers, at taking a sort of like budget of the universe, and we can say that 5% of the universe is stuck into stuff that's you and me. We call this baryonic matter. Don't worry about the name, but it's just stuff that you and I, and potatoes and Beyonce are made of. These things this is baryonic matter. We know that about 25% of the universe, give or take, is dark matter. And the rest of the universe is this thing called dark energy. And these are slightly different things. They're not super related. They're actually two different questions. And it's a longer story. If you want to talk about dark energy, we can. But at the end of the day, that's a big open question. Like we would, if we find out what dark matter is, in principle, we will answer that question. To know what at least 25% of the universe is made of.